Welcome to Module 2.3, Blockchain Scaling, On-Chain Solutions. In this module, we'll explain why scaling is necessary and examine notable on-chain scaling solutions. We've just learned the blockchain trilemma in the last module and understand the inherent trade-offs among three core properties of decentralized networks: decentralization, security, and scalability. As blockchain adoption grows, so does the demand for faster and more efficient blockchain networks. Scaling solutions are needed to accommodate the increasing number of users, transactions, and applications built on top of a blockchain without compromising security and decentralization. For example, Bitcoin can process around 7 transactions per second, while Ethereum can handle around 30 transactions per second as of mid-2023. That's significantly lower than the tens of thousands of transactions per second handled by centralized payment platforms. Moreover, many blockchain networks frequently experience significant congestion when demand goes up, resulting in slow transaction processing times and increased fees. Scaling solutions aim to improve transaction speed, transaction throughput, and overall network performance. Transaction speed refers to the time it takes for a transaction to be processed, validated, and confirmed by the network. Transaction throughput refers to the number of transactions that a blockchain network can process within a set amount of time. This is usually measured in transactions per second, also referred to as TPS. Blockchain scaling solutions can be broadly categorized into on-chain and off-chain solutions, also referred to as Layer 1 and Layer 2 solutions, respectively. This module will focus on on-chain, or Layer 1, scaling solutions. On-chain scaling solutions attempt to make adjustments to the base layer protocol of a blockchain to enhance its scalability, such as increasing block size, reducing block time, sharding, and consensus algorithm improvements. These Layer 1 scaling solutions seek to improve transaction speed and transaction throughput by making changes to the blockchain directly. Let's take a closer look at each of these solutions to examine their benefits and drawbacks. As we've learned in the first section of this course, a blockchain can accommodate more transactions within each block by increasing the block size, which increases the overall throughput. Similarly, reducing block time can increase the number of transactions processed per second. But these two methods have a few critical trade-offs. They usually require a fork, which may split the community. Such a split can be disruptive. Moreover, larger blocks can lead to higher resource requirements from miners, which leads to increased centralization. Shorter block times can lead to a higher rate of orphaned or stale blocks, as multiple miners may solve a block simultaneously. This can decrease overall network security. All of these factors need to be considered before embarking on these solutions. Next, let's take a look at sharding, a technique that has existed in the field of distributed databases for a long time and has been successfully employed to improve the scalability and performance of large-scale data management systems. In blockchains, sharding involves dividing the network into smaller parallel subchains, or shards, that can process transactions independently. Sharding can be compared to dividing a large company into smaller teams to work on specific tasks. It effectively distributes the workload across multiple nodes and therefore improves the overall throughput. This solution also comes with a few challenges, one of which is maintaining the security and integrity of the network. Splitting the network into shards can potentially make it more vulnerable to attacks. Ensuring cross-shard communications is another challenge, as transactions and data may need to be transferred between shards to maintain consistency. There are solutions proposed to address these issues, including the use of random sampling and cross-shard messaging. Lastly, implementing more efficient consensus algorithms can also help scale the blockchain. As we've discussed in our previous modules, the consensus algorithm determines how a blockchain network validates transactions, agrees on a single version of the truth, and maintains security. developers can improve the performance, efficiency, and scalability of a blockchain network without compromising security or decentralization by optimizing or introducing new consensus algorithms. For example, Ethereum transitioned from a proof-of-work consensus mechanism to proof-of-stake in 2022. Besides being more environmentally friendly, proof-of-stake allows for faster transaction validation and ultimately improves scalability and enhances security. Delegated proof-of-stake is a consensus algorithm that elects a small number of validators for validating transactions and creating new blocks. This can achieve higher throughput and faster transaction confirmation times, but could potentially lead to centralization. On-chain, or Layer 1, scaling solutions are a crucial aspect of scaling blockchains and make the technology ready for mass adoption. But as we've discussed, each of these solutions comes with drawbacks. In the next module, we'll delve into off-chain or Layer 2 scaling solutions.